Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. In this video, I'm going to tackle part B of this two-part question, and it follows on from a video I just did on part A, where we proved the nth derivative of sine ax plus b. So part B says hence or otherwise find the nth derivative of sine squared x cos squared x with respect to x. And that hence at the beginning here hints that we're going to need to use the result that we've just shown in part A. So that kind of hints that if we want to get this nth derivative of sine squared x cos squared x, we're first going to have to transform it, use some trigonometric identities to get it into the format sine ax plus b, because once we do that, we'll then be able to apply this result from part A. So here I'll just note what we need to prove, or actually here we're not proving, we're finding the nth derivative, so dn dx to the n, so with respect to x, of sine squared x cos squared x. So that's what we need to find, and we know that inevitably we're going to make use of this result that I showed in part A in the previous video. So as I mentioned, we need to get this into the format of sine ax plus b. I think to get started, maybe what I'll do is just over here as a preliminary step, let's kind of say sine squared x cos squared x. I think the first thing we can do that might be helpful is to just write this as sine x times cos x all squared. And I think the reason that's helpful is this sine x times cos x, we could write that as being sine of 2x divided by 2. So that's all squared. And the reason I can say that is because of the identity sine 2x equals 2 times sine x cos x. So we could then kind of square the top and bottom, and we'd end up with a quarter times sine squared 2x. Now at this point, the first path I went down that didn't prove helpful, but I thought maybe I could use the chain rule here, because I've kind of got a sine ax plus b, where a in this case would be 2 and b would be 0, but I've just got it squared. But because we're dealing with the nth derivative, when you're doing the chain rule, you kind of have to do the nth derivative of the outside and then the nth derivative of the inside, and we haven't really got that, so we need to keep going with this sine squared 2x to get it into that format sine ax plus b. So what I might do is we'll now do another side step where we're gonna try and simplify what is sine squared 2x. And again, I think we can start by kind of writing this kind of sine 2x identity. I think we can start with this and see how we can perhaps get to the place we need to get to. So what I'm going to do is replace sine 2x here with 2 sine x cos x, which we know is squared since we're sine squared 2x. And so I'll now almost do the reverse of what I did here and put the squares through. So we'll do 2 squared is 4, sine squared x cos squared x. And what I'll do here is I'm going to first get this all into cos squared x, because I know we're going to end up in a place where we can get a kind of cos x without any squares in it, and then get it back to sine using similar techniques to what we did in part A. So from here, 4 sine squared x cos squared x, what I'll do is I'll write that as 1 minus cos squared x times cos squared x, and that's using the identity sine squared x plus cos squared x is equal to 1. So I've just kind of then brought the cos squared x over to get sine squared x by itself and then inserted that. So now what I'll do is I'll just expand that out. So we'll get 4 times cos squared x minus cos to the power of 4x. And then I'll just expand out the 4. So we'll get 4 cos squared x minus 4 cos to the 4x. And what I'm going to do here is I'm going to say plus 1 minus 1. So I haven't actually changed anything, but I want to get a kind of minus 1 in there because I want to get this in a format where I can eventually get it as a perfect square. So what I'll do now is I'll just take this positive 1 and write that out the front. And we'll have minus 4 cos to the 4x. Plus 4 cos squared x, and then we've got minus 1 at the end. And you can kind of see how I'm pretty close to having first one squared, twice the product, last one squared, where it's cos squared as I guess the variable. But what I kind of need to do first is I need to kind of get a minus throughout. So we'll write this as 1 minus bracket, and that would give us the 4 cos to the 4x, since that's already got a minus. Then it will be minus 4 cos squared x plus 1. And you see, if I was to put the minus through, I'd get back to where I was here. But now you can hopefully see that if I can now write this as 1 minus 2 cos squared x minus 1 all squared. Because you can see if I then expanded this, I'd get the first one squared, 4 cos to the 4x, minus twice the product, which would be minus 2 times 2 is minus 4 cos squared x, plus 1. So this is the perfect square. Now what I can say is that is 1 minus cos squared 2x, or in other words, this bit inside here is cos 2x. And I can say that since cos 2x, the identity that you probably know is that cos 2x is cos squared x minus sine squared x. And that I could write as cos squared x minus 1 minus cos squared x, using this same identity here. And that, if I expanded this, we'd end up with minus 1 plus cos squared x. So we'd have 2 of the cos squared x minus 1. And that's exactly what we've got here, 2 cos squared x minus 1. So that's why I can now replace that with cos 2x that we've got squared. Alright, now what I'm going to do, this probably wouldn't leap out at you as being obvious, but I'm going to write this 1 as a half plus a half, which adds up to 1. And I'm also going to write this cos squared 2x, this minus cos squared 2x as minus a half times 2 cos squared 2x. And we'll see why that's going to help us soon. We're going to then get this into the form where we can again use an identity, specifically this identity, to kind of get rid of this squared. I might have to turn over though, just because I'm running out of space here. So what I might do is I'll just kind of turn over and pick things up. So where we're at is that sine squared 2x can be written as, what I'll do now is I'll factor out this half. So I could say it's a half bracket, and we'll have 1 being first half. And then what I might do is I'll then say that's minus the 2 cos squared 2x and then plus the other half. So minus 2 cos squared 2x and then plus 1. And that will then expand out to get us back to here. But now what I'll do is I'll write this as then a half 1 minus 2 cos squared 2x minus 1. And hopefully you see this is in the format of 2 cos squared x minus 1, but instead of x, it's 2x. So what we can actually say is that that is equal to a half times 1 minus cos 4x. And how I'm getting there is I'm saying cos 4x is essentially cos of 2 times 2x. So it's kind of cos of 2 times something where that something is 2x instead of x. So that means if I kind of take this result, cos of 2 times something, it's equal to 2 cos squared of that something minus 1. And here the something now is 2x. So I can say it's 2 cos squared of 2x minus 1. And that's exactly what we have here. 2 cos squared 2x minus 1. So that's why I can replace that with cos 4x. Alright, so now what we can do is we can bring those two side steps together and we can say, therefore, sine squared x times cos squared x, which is ultimately what we want to differentiate, is equal to, well, we had it as a quarter of sine squared 2x, so it's going to be a quarter times sine squared 2x, which we know, or we've just worked out, is a half 1 minus cos 4x. Alright, so I can now bring this quarter times a half together as 1/8, and I can expand these brackets to be 1 on 8 minus 1 on 8 cos 4x. And now I'm going to use a very similar technique to what I did in part A. And I should mention, I didn't mention at the beginning, but if you haven't watched part A, it would be a good idea to go and take a look, because as you've probably noticed, part B follows very closely on from part A. So getting your head around what went on in part A will really help you with following this, particularly because I'm using some similar techniques, especially at this point right now. I'm going to essentially use the techniques that really helped us in part A. So what I'll do is I'll write this as 1 on 8 minus 1 on 8 cos to the negative 4x. And the reason I can say that is because cos of negative x equals cos of x, the even nature of the cos function. And now I can write that as 1 on 8 minus 1 on 8 times sine of pi onto plus 4x. And what I've used there is the fact that cos of x is equal to the sine of pi onto minus x, or 90 degrees minus x, you might see that as. And so here I've done the pi onto minus 4x, which is why it becomes added. So essentially, just writing this in the kind of ax plus b format we need, we get 1 on 8 minus 1 on 8 sine 4x plus pi onto. And hopefully you see that's ax plus b, where a in this case is 4 and b is pi onto. Alright, so now we can bring this all together. So we can say, therefore, the nth derivative with respect to x of sine squared x cos squared x, what is that equal to? Well, that's equal to the nth derivative with respect to x of this whole thing here. So 1 on 8 minus 1 on 8 sine 4x plus pi on 2. Now, we can kind of break this up to say it's the nth derivative of 1 on 8 minus the nth derivative of 1 on 8 sine 4x plus pi on 2. This first bit, the derivative of a constant is just going to disappear. So this is going to simplify to minus 1 on 8. We can bring that out the front. Times the nth derivative with respect to x of sine 4x plus pi on 2. And now what we can do is we can note that this is in the format of sine ax plus b, where a is equal to 4 and b is equal to pi on 2. And what I might do is I'll just turn over, and maybe what I'll do is I'll just note the result from part A. So let's note from part A, we know that dn dx to the n of sine ax plus b is equal to a to the n sine ax plus b plus n pi on 2. So that's a to the n times sine ax plus b plus n pi on 2. So applying that, we can say, therefore, the nth derivative with respect to x of sine squared x cos squared x is equal to negative 1 on 8 times, and here I've got a is 4, b is pi on 2, so I can say a, which will be 4 to the power of n times sine, and we'll get 4x plus b, or plus pi on 2, plus the n pi on 2. Alright, and that we can write, I can think of 4, maybe I'll just write this out in a step. So 4 I can think of as 2 squared, and then to the power of n means it'll be to the power of 2n. And 8 I can think of as 2 cubed times sine of 4x plus, I've got n pi on 2 plus 1 pi on 2 means it will be n plus 1 pi on 2. And this I can write as equal to negative 2 to the 2n minus 3 times sine 4x plus n plus 1 pi on 2. And that's the result. That's the answer for the nth derivative of sine squared x cos squared x. And if you wanted to, something I did just to check that I hadn't made a mistake along the way is I opened up a spreadsheet and I entered this in for n is equal to 1. And then I worked out the derivative of, or the first derivative of sine squared x cos squared x, just using the product rule. And I made sure that they gave me the same result for various angles, various values of x. So testing it for n is equal to 1 is something you could do if you wanted to, just to double check. The good news is it did give the same result, so that gives you some comfort that this is the result. And I guess in theory you could keep trying and do higher derivatives. I didn't myself, so I'm not sure how messy it might get. But ultimately, having done this work, we can now use this. We could pick any value of n. We could get the first derivative, second derivative, third derivative, whatever derivative we wanted, using this result. So it's quite handy, quite a good one to have, to have demonstrated and worked out. I think this question was quite a lot of work involved, and I think upon reflection, whoever wrote this question, perhaps they could have given a bit of scaffolding, and by that I mean providing a bit of guidance, because there are so many trigonometric identities that you could apply, and you could end up going down so many rabbit holes. I mean, I went down one where I tried to use the chain rule and it didn't really work for me. But perhaps a kind of extra part where instead of having part A and then just part B, you could have had an intermediary part where you were asked to show some result for sine squared 2x. Maybe it could have said something like, show that sine squared 2x is equal to a half 1 minus cos 4x. And then perhaps having that as a preliminary step, it might have helped a lot of students kind of know what to do, because without much guidance, it's quite hard to kind of work out how to manipulate this sine squared x cos squared x. I mean, we know that we needed to get it into sine ax plus b to be able to use part A, but I can kind of imagine many students would kind of end up going down rabbit holes and spending so much time not getting anywhere and potentially giving up, because as you can see, there's a lot of steps that are required to get you from this sine squared x cos squared x to then sine squared 2x, and from there to having something in a cos 4x that then lets you get it back to sine ax plus b. I mean, a lot of steps there, a lot of opportunities to make mistakes. And if you look at it, I've had 1, 2, 3, 4, 5 different trigonometric identities that I've had to make use of. And, you know, that's not easy. So can definitely see why many students might struggle with a question like this. But hopefully you were able to follow along with all that. If you did find it helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.